Hi, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry, from engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Today we're going to be looking at a heavily requested video by NileRed called Making Superconductors. Now, superconductors are characterized by almost no resistance, and they have the potential to generate very powerful magnetic fields, which could be used for something like nuclear fusion. Maintaining that magnetic field could give the reactor the confinement time it needs to maintain a steady state nuclear fusion reaction. It's all very exciting stuff. Let's see him trying to make one at home.
2 years ago, I think I was doing research for my ferrofluid project, and I ended up watching a short video about superconductors. I don't remember exactly what video it was or where I even saw it, but I do clearly remember that it kind of blew my mind. They showed that if a magnet is dropped on top of a superconductor, it just floats there like some anti-gravity magic.
Yep.
At first, I thought that it was just carefully balancing there or something, but it could be easily pushed around to different positions. On top of this, what was even cooler in my opinion was that when it was gently nudged, it was able to just freely spin around. After seeing this, I immediately went to Google to see how hard it was to make a superconductor myself. Based on what I saw, it seemed like it was possible, but it also seemed like it was really complicated.
I like that Google just gives you step-by-step instructions. I love the age in which we live.
So I kind of procrastinated for the next year and a half until this past January, when I decided to finally commit myself to it. When I looked into it a bit more, I found that superconductors can technically be made from a lot of different materials. However, for most of them to work, they need to be cooled to ridiculously low temperatures. For example,
Ridiculously low as in almost absolute zero, as in you need to keep it continuously cool. That could take a lot of effort.
just mercury can apparently be a superconductor, but only when it's lower than negative 269C, which for me is just impossible. The superconductor that I saw in that video, though, was called a YBCO superconductor, and it didn't have to be nearly that cold. It only had to be lower than negative 181C, which I could easily do by just soaking it in liquid nitrogen. I did a bit more research, and I found that there were other ones that also worked with liquid nitrogen. However, I couldn't find much info on how to make them, and from what I did find, they all seemed to be a bit more difficult. So, YBCO really seemed like it was the best option. Okay, so I committed to making YBCO, and now I had to put together some sort of procedure.
Putting it into Google, or let's see how old this video, so maybe not ChatGPT, write a procedure for me to make a superconductor and try to do it safely. Oh, that's awesome.
Like before, I reached out to Google for help, and the first result that I got was probably the best one. It was a video by Ben over on the channel Applied Science, and he was able to make a working superconductor. He covered almost all the essential info about the process, and it was extremely helpful. The only thing that I wanted to change was the final shape of the YBCO. Ben had just used a crucible as a mold, so it wasn't exactly the most beautiful looking thing, but I wanted mine to be some nice and pretty pellets, just like I had seen in that video. In the description, he also gave a link to the full-length procedure that I assume he followed. It was probably the most detailed procedure on the internet, and it made everything seem relatively straightforward. So, I decided to do exactly what they did, except on a larger scale.
There is a whole art and science to writing in effective procedures. There's certifications you get. I know people, when they say for starting up a nuclear power plant, everything from how easy it is to read, how easy it is to follow, and even getting like your spacing right, and where to make your page break so you're not in the middle of a step, and then you turn to the next page and it's like, oh, by the way, we need you to hold that for 5 minutes or something like that, just as an example. So there's so much human factors engineering in procedures that you know you've done an excellent job when you can make something as complicated as making a superconductor or starting up a nuclear power plant be followed extremely easy. I remember in one of my leadership training classes, we went over purposely terrible procedures that told you how to build a little Lego together just to illustrate and drive the point on what bad procedures look like and how we should stay away from them.
However, when I actually sat down and started doing some calculations, I realized that none of their numbers made any sense.
That's awesome.
YBCO is called YBCO because it's a combination of yttrium, barium, copper, and oxygen. However, it's also sometimes called yttrium-123 because of
Yttrium's another one of those materials that's used in radiotherapy to treat cancer. You can actually be injected into the blood, and it's a beta emitter, and those betas can help. They go into blood vessels, and the blood transports them to the tumor, and it gets and the betas end up damaging some of those cells, so it cuts off blood supply to the tumor. It's a fascinating type of treatment.
the ratio between the components. There's always 1 yttrium, 2 bariums, and 3 coppers. In this case, though, they don't seem to be using this 1-to-3 ratio, even though they say that they are. On top of this, they did a whole bunch of seemingly pointless calculations, and they also used a number that was blatantly just wrong. This isn't to blast them or anything, though, because calculation errors happen all the time, but it meant that I couldn't rely on what I had here. It was very possible that the rest of the info was still good, and it probably was, but after seeing this, I really just didn't trust it.
Can't say I blame him. If you see something wrong with the procedure, or a lot of times this happens with shift turnovers about a procedure being marked up or something, I find it's less work to just start from scratch.
So, I scoured the internet for a new procedure, and a few days later, I was thankfully able to find this one. It wasn't nearly as detailed and it didn't have any photos, but it actually gave numbers that were accurate. Now, before I could actually get started, I had to buy a bunch of chemicals. The first 2 were yttrium oxide and copper nitrate, and I was able to find both of them on eBay. I also needed barium nitrate, but I wasn't able to find it anywhere online. So, I unfortunately ended up just overpaying for it and ordering it from a chemical company. The last thing that I needed was citric acid, which is commonly used in food, so it was really easy to find, and I got 2 pounds of it from Amazon.
There you go.
At this point, I had all the ingredients that I needed, but I started to worry about the purity of the eBay chemicals. The copper nitrate was all nice crystals and it looked okay, but I really wasn't sure about the yttrium oxide. The eBay listing said that it was over 99% pure, however, you can never really trust those claims.
Where you want to get your obscure science stuff, eBay's the place to go.
So unfortunately, I was going to have to purify it, and the best way that I found was to convert it to yttrium nitrate. To do this, I added 200 mils of water along with about 100 mils of concentrated nitric acid. I let it stir for a couple minutes, and then I started adding some of the yttrium oxide. The amount that I added here was kind of random, but when I eventually felt that it was enough, I turned on the hot plate. Right now, nothing was really happening, but when it got hot enough, the yttrium oxide suddenly started reacting with the nitric acid. This quickly turned it all into yttrium nitrate, which, unlike the oxide, was soluble in water. This caused the solution to slowly clear up, and after this, I just kept adding the oxide whenever it looked like it was fading. It eventually got to a point where it stopped clearing up, and this meant that all the nitric acid was gone. I then added a bit more nitric acid, just enough to destroy the extra oxide. This caused it to clear up again, but it was still a bit cloudy, and there was a whole bunch of solid junk that was floating around. I had no idea what this was, and it was all just some sort of impurity. So, it was apparently a good thing that I decided to clean it up. To get rid of it, I filtered it all through some cotton and sea light, and this left me with a nice and clear solution. I then put it all back on the hot plate, and I got rid of most of the water. I honestly didn't know exactly how much I had to get rid of, and I just went until it was roughly half the volume that I started with. After that, I took out the stir bar, and I waited for it to cool to room temperature. I let it sit like this for a few hours, but nothing really happened. So I started poking at it a bit to force the yttrium nitrate to crystallize. I wasn't sure if this was going to work, but it did, and there were a bunch of small crystals that formed around the stir rod. I then gently stirred the whole thing, and I let it sit overnight. The next day, there was a whole bunch of yttrium nitrate at the bottom, and I broke it into smaller pieces.
That's fascinating. Patience definitely seems to be a virtue when doing these sort of experiments, because for a while it just really didn't look like anything, but good on him for letting it sit overnight, being patient, stirring gently. That's good. Without a procedure, I wouldn't know.
To separate it, I poured it all into a vacuum filter, and I was eventually left with some clean and fluffy crystals.
That's cool.
It was all still covered in water though, and to fully dry it up, I put it all into a vacuum chamber that had some drying agent at the bottom. I pulled a full vacuum on it, and then I took it out a few days later. What I had now was some dry and crunchy yttrium nitrate. This of course wasn't the oxide that I had started with, and if I specifically needed it to be the oxide, part of the purification process would have been converting it back. But conveniently, turning the oxide into the nitrate is actually the first step in a lot of YBCO procedures, including the one that I was following. So, this whole purification was kind of just a slightly more complicated first step. At this point, it was still a bit wet, so I put it all back into the vacuum chamber and I let it dry for a few days. After this, I had some dry and pure yttrium nitrate, and now I could actually start making the YBCO.
Wow, all that just to make sure it's pure enough. I really admire his dedication to these experiments.
To do this, I started by adding 225 mils of distilled water, and I turned on the stirring. Then into this, I dumped in 72.48 grams of the copper nitrate. It immediately turned a really nice blue, and I waited for it all to dissolve. When I came back to it a few minutes later, it was still a bit cloudy, probably because there was a bit of copper carbonate in there. This wasn't much of an issue though, and I just added a couple drops of nitric acid to convert it all into copper nitrate. This caused it to all quickly clear up, and the next thing that I added was 52.27 grams of the barium nitrate. This, however, really wasn't very soluble, and I had to heat it a bit with the hot plate. I let it stir for about 20 minutes, and it had gotten quite hot, but there was still a decent amount of solid stuff. This was fine though, and I just went ahead and added 38.3 grams of the yttrium nitrate that I had just made.
I always get mesmerized by the little vortex from these spinning chemicals as he stirs them, and I find these videos very relaxing.
I then waited until it looked like all the yttrium had disappeared. However, exactly when that happened was a bit hard to tell because there was still so much barium floating around. When it eventually seemed okay, I added the final ingredient, which was a bunch of citric acid. I let this stir for about 20 minutes, and then I checked the pH. The red color told me that it was quite acidic, and it was probably around a 1 or 2. What I had to do next was neutralize this and bring the pH up to between 6.5 and 7. To do this, I had to use ammonia, and I had just recently bought a fresh new bottle of it. The moment that it was added, it started reacting, and it turned a much darker blue. It also generated a lot of heat, and it was causing some of the water to boil.
Cool.
So, I had to make sure to add it slowly.
And now it's dark.
After adding a decent amount, I let it stir for a few minutes, and I checked the pH again. It now looked like it was around 5, which was better, but I still had a bit to go. So from here, I just kept adding small amounts of ammonia and checking the pH. The first major reaction that was happening here was between the basic ammonia and the citric acid, and it was turning it all into ammonium citrate. It was also reacting, though, with the yttrium, barium, and copper nitrate, and turning them into hydroxides. The copper and yttrium hydroxides then reacted with more ammonia to form dark blue complexes. I don't think the barium was complexing with the ammonia, though, and it was instead forming a complex with the ammonium citrate. However, I really don't know that for sure, and I had a very hard time finding any decent info about this reaction in general. It was really hard to tell with these cheap pH papers, but it eventually looked like it was between 6.5 and 7. To see if all the barium had disappeared, I took out a small sample, and it looked okay. There was a small amount of junk, though, so I quickly poured it, all through a coffee filter. When this was eventually done, I got rid of the funnel, and now it was time to turn all of this into the YBCO. To do this, I had to split it up into a bunch of smaller portions, and I poured 50 mils into another beaker. I then turned on the hot plate, and I waited for the water to evaporate. About 30 minutes later, I was left with this nasty brown mess. Based on what I had read and seen, this was kind of what I expected. I still wasn't sure, though, and it was just so gross that I honestly started worrying that I had messed something up. I actually
can
started
see
thinking
that.
that I was going to have to start over, but it turned out that I was just being impatient.
Whoa, it's burning.
At first, the sound caught me a bit off guard because it was way louder than I thought it would be.
Check
I also didn't
that
think that it was
out.
going to be so slow or that it would grow like that. It was a pleasant surprise, though, and I honestly think that at least visually, it's one of the coolest reactions that I've ever done.
That is crazy. I was not expecting that.
When the reaction was over, the beaker was still very
It kind of reminds me of that mercury and aluminum amalgamation. I'll pin that in a comment below. That one was pretty cool too. But this one I was not expecting.
hot, and I put it somewhere to cool down. Then, into a new beaker, I added 75 mils instead of 50. I was trying to use more because I had to keep repeating this reaction for a total of about 500 mils.
Interesting he keeps saying mils. I was taught a mil was 1,000th of an inch rather than a milliliter, but I suppose that's a regional thing.
I was hoping that by using 75 mils, I wasn't overdoing it, and that it could just make things go a bit faster. Now, in terms of what was actually happening here, it was called a citrate pyrolysis reaction. Just before, when I had added all the ammonia, it had turned all the metal nitrates into hydroxides, but it had also made ammonium nitrate. This was a really strong oxidizer, and all the ammonium citrate was a good fuel. When the temperature was high enough, it triggered a reaction between the two, and it caused it to burn. All the yttrium, barium, and copper hydroxides were mixed in here as well, though, and the heat of the reaction caused them to decompose. It turned them all into their oxide forms, and it also made a lot of water vapor, which was why the side of the beaker kept fogging up.
Love that he explained it. That's so cool. Love the little chemical equation explanations too.
When I first did this reaction, I thought that it was making YBCO, but I don't actually think that's the case. I think that it was mostly just making a really good mixture of the metal oxides. I was a bit worried that using the 75 mils might be a problem, but it turned out to be mostly fine. The only thing that I didn't like was that it grew out of the beaker. In this run, it didn't end up being an issue, but in another one, it could grow weird and maybe cause some of it to fall out. So I went back to doing it with 50 mils, and to make it go faster, I ran a couple others at the same time. It was kind of fun, and it felt like I was running a small little YBCO factory. I was eventually almost done, but with the last little bit that I had, I decided to try something different. In all the other runs, there was a bunch of water vapor that clouded the beaker, and it made it hard to see. So, I wanted to see if I could fix this by instead doing it in a dish. It was definitely a lot clearer, but I kind of knew that it was going to be a bit of a failure. There was just no way that it was all going to stay in the dish.
Yeah.
What was worse, though, was that this dish wasn't made of borosilicate glass, which meant that it wasn't great at handling big changes in temperature.
Oh no.
Despite this, I was hoping that it would still be
It's
able
all
to
flaky.
survive, but it did not. Because it exploded before it was done reacting, I didn't trust the quality of the stuff that was made. So unfortunately, everything that I just made here was kind of just garbage. That didn't really matter though, because I had more than enough good stuff from all the other runs.
I like that he keeps in the times he made something and something broke or whatever, and he left that in there explaining it just to show you the level of trial and error that goes with making something like that. I really admire that he puts that in there, because some people are just like, well, I'm not going to show my mistakes, for lack of a better word. The way I see it, they're learning opportunities, but I think that's really cool.
What was interesting was that it looked like I had an insane amount of it, but it was just really fluffy. The moment that I just even barely touched it, it just collapsed. I then mixed it around to reduce the volume even more, and I combined everything that I had from all the runs. So at this point, like I said before, I don't think that I actually had any YBCO yet, and it was just a mixture of the yttrium, barium, and copper oxide. To turn it into the YBCO, it had to be heated to a very high temperature in the presence of pure oxygen. Most procedures said that they used something called a tube furnace, but when I went online to buy one, they weren't exactly cheap. They were all way too expensive, and I figured that instead, I would have to modify my little tabletop furnace.
I like that they're all on eBay too. That's just perfect.
This was exactly what Ben had done, and he had modified his furnace and rigged it to an oxygen tank, so it should have been okay. Though, I found some tube furnaces being sold on Alibaba that were way cheaper. I spent a while researching all the different models, and I ended up getting this one, which had a nice touchscreen. The total price was about $2,000 US instead of like $5,000 or even more, and I figured it was worth trying out. I guess
love what he invests into these projects, man.
And I didn't know if it was even going to work very well. I was excited when it arrived a few weeks later, but I also got a call telling me that it wasn't all in one piece.
I was calling about your package. Are you coming to pick it up?
Oh no.
Yeah, I'm actually going to be there very shortly.
Okay. The only problem is that it's damaged. It's quite severely damaged. Yeah, it seems that they shipped it in a crate, and the crate has come apart.
Huh.
So, I'm not sure, like, what you want to do. I mean, you'd have to look at it yourself, I guess.
After hearing this, I was pretty much expecting to just see a pile of rubble. However, it was somehow still completely fine, and there was only one minor scuff on the bottom, which I was okay with. I
guess he was just freaking out because the crate broke or something. Okay.
Make sure that it actually worked though, so I brought it back to the lab and I plugged it in. I then clicked the button and it seemed to be totally fine. But then it suddenly turned off and I started to smell something burning. There was also some nice smoke coming out the back of it, which isn't something that you usually like to see with electronics. I was really disappointed, and I figured that it was damaged in shipping or something, but then I realized that it was entirely my fault. When I was ordering it, they asked if I wanted to run it on 120 or 220 volts, and I totally forgot that I said 120.
Oh, wow. Getting the units wrong can be expensive. Yeah. They've seen that with a lot of the procurement with the new nuclear plants, Vogtle units 3 and 4 in the US, and so many of those pieces of equipment were manufactured in foreign countries and they were brought in, the unit difference between gallons to liters, pounds and kilograms, all that I've heard of. I was never directly involved with this project, but I've heard from some of my industry peers that they ran into some unit conversion issues. And we all know that unit conversion issues ended up destroying a Mars rover. Man, I hate that. I actually, on the subject of units, when I was in college, I learned everything using the metric system. And then when I went to work in a nuclear plant in the US, I had to reconvert myself to everything using the imperial units, which, yeah, I wish the US would just use the metric system.
I also forgot to tell them to put an American plug on it instead of the standard 220 Chinese one.
Oh,
so,
yeah.
Based on the plug and some terrible memory, I had just assumed it was 220, and I plugged it into my 220 line. This was probably one of the dumbest mistakes that I've ever made, and it was very possible that I destroyed the furnace.
I appreciate the vulnerability in showing a mistake like this on camera, on your channel. That's very good. I might have been too embarrassed. But yeah, that's a real mistake that we've all made. Anything involving unit conversions, sure.
I honestly panicked a bit, and despite knowing not very much about electronics, I took it apart to see what was broken. The first thing that I found was this broken capacitor, which had popped open at the top of it.
Yeah.
It had also spewed all of its capacitor goo onto the board
Capacitor goo.
above it. The only other thing that was obviously dead was the voltage transformer, and when I took it out, I could see that it was all melted. I assumed that I was going to have to change the capacitor and maybe some of the other things on the board, but I apparently got really lucky. When I contacted the company, they were surprisingly super helpful, and they told me that the part of the board that broke didn't actually matter.
Well, that's good.
So, I technically didn't even have to repair this board at all, and all I did was take off the broken capacitor. Now, the only other obvious problem was the transformer, and with the help of my dad, I swapped it out for a new one. We then plugged it in to the proper 110 socket, and it didn't immediately light on fire, which was a good sign. The real test, though, was to actually turn it on, and I was genuinely really nervous.
Love it.
But by some amazing luck, the furnace was apparently saved. I then did a few heating tests on it just to be sure, and it was completely fine. So apparently, luck was on my side, and I didn't have to buy a new furnace or anything. It did take a few days to troubleshoot and fix everything though, which wasn't ideal. But either way, I can now get back to the actual project and try to make some YBCO. To do this, I dropped a quartz tube into the furnace, and I filled it with the oxide powder. I had no idea how much I could add, and I just put an amount that I felt was good, and it wasn't really based on anything. I then took out the piece of paper that was just being used to keep the end of the tube clean. After that, I slid in these end piece things, which would help seal the furnace and prevent the heat from leaking out. I then rigged the tube with some metal pieces that would let me attach the oxygen. With all that done, I closed the furnace, and I connected the oxygen line. I also opened the oxygen tank, and I adjusted the flow rate. I spent a lot of time trying to figure out how much oxygen I had to use, but I couldn't find any decent resources. So, this was kind of based on nothing, and I just went with 50 mils per minute.
I love all the firing from the hip with this project. I mean, that's kind of what you have to do if you don't have a procedure and no reliable resources. I couldn't imagine doing something like that with a nuclear plant. They're always very prescriptive with procedures and how much you, like for instance, when you pull control rods, there are entire books and data tables about how much reactivity, how much it's going to increase reactor power by versus what phase you are in core life, because this sort of thing changes based on how much of the uranium fuel has been burned up, which makes sense. And there's always an elaborate reactivity brief every shift or every time you change. If conditions change, there's always a briefing if you're going to do something that has the potential to affect reactor power or directly affect reactor power on purpose. Yeah, I couldn't imagine the whole, let's pull control rods 3 steps and just see what happens. Except, of course, in the simulator when we're all just doing initial training and learning how to do stuff. But that's different. That's all fun and games.
After that, I turned on the furnace, and I checked the heating curve to make sure that it was the right one. I'd set this up beforehand, and it was pretty simple. Over an hour, it would be slowly heated to 920C, and then held there for 10 hours. After that, it would be slowly cooled at 50C an hour until it was room temperature. This whole process should cause the oxide powders to fuse together and form the YBCO. The slow cooling part would also let it crystallize, which was very important. I went ahead and started it, and I came back to check on it about an hour later.
Cooling down too quickly, this can be applied to anything, including like a pressure vessel in a nuclear plant. Cooling down too quickly can have something fracture based on like brittle fracture mechanics, can cause cracking, that sort of thing. So if you want it to crystallize good, you're going to want to cool it down slowly. There's also, when you cool down, or heat up for that matter, a nuclear power plant, you take cool down logs or heat up logs. There's limits such as 100 degrees per hour is the cool down limit. And keep in mind that's degrees Fahrenheit. Yes, imperial units, I know, but that's what all the meters and stuff say. It's probably too expensive to to get all that sort of stuff replaced. But yes, wouldn't be the case here, but thermal shock is it's even more of a hazard when you have the excessive cool down and sudden pressurization. That's pressurized thermal shock. That's one of those things that is guarded against, has been tested extensively, and safety systems have been designed to operate to prevent the pressurized thermal shock sort of a brittle fracture function that can happen on any large pressurized vessel, including a reactor vessel. Because if you break a nuclear reactor vessel, that unit's never getting started up again, I'm sorry to say, because a lot of the cases, we don't know how to make those anymore. Even if that were to happen, everything would be contained in the reactor building. That thing's never producing electricity again.
At this point, it was at the max temperature of 920C, and on the outside, it didn't look like much was going on. If I looked in from the side, though, I could see that it was glowing red. It was gonna have to cook like this for another 9 hours, and then it would be slowly cooled over 18, and I just left it overnight. The next day, I opened the furnace, and the first thing that I noticed was that the powder was a lot blacker, and that it had also shrank. I then took off most of the metal attachments on the sides, and I pulled out the white blocks. To get it out of the tube, I carefully pushed it with a glass rod.
Delicate operation.
What I had now was definitely more dense than before, but it was still pretty fluffy and fragile. In theory, though, this should have been YBCO, and I wanted to see if it were able to superconduct. So, I poured some liquid nitrogen into a dish, and I waited for it to cool down. I then dropped in a piece, and I waited for that to cool as well. When everything looked nice and cold, I dropped a piece of a neodymium magnet on it, and it clearly didn't work. This was honestly a bit disappointing, but it also wasn't surprising. The first problem was that it was still too light and fluffy, and there wasn't actually very much here. The second, and probably bigger issue though, was that I don't think it was oxygenated enough. YBCO always has the same ratio between the yttrium, barium, and copper, but it's able to vary between 6 and 7 oxygens. However, it's only able to superconduct in the 7 form, and what I had probably still contained a lot of the 6 form. To fix both these problems, the YBCO is usually compressed into pellets and then put back into the furnace and heated again with oxygen. So, that was exactly what I had to do next. To do this, I started by adding it all to a mortar and I ground it into a fine powder. I think in Ben's video, after he did this, he just put it all into a crucible and heated it again, and it ended up working. However, like I said before, I wanted mine to be some nice hockey puck looking things.
There you go.
To make this happen, I needed a die set, which would let me crush it and shape it. I also needed a hydraulic press, and I had bought both of these things over a year ago. So, basically, I had everything that I needed, but I had no idea how much powder to actually use, and I just ended up putting in all of it. Then on top of it, I added a metal spacer thing and a pushing rod, and I brought it over to the hydraulic press. For safety reasons, I put the gate in front, just in case something decided to explode under the high pressure.
Love the safety part of his videos.
I then started pressing it, and I brought it up to about 8 tons. I let it sit there for a few minutes, and then I released the pressure, and I took off the bottom piece. I could see the nice pellet that I'd made, and now I had to get it out. So I flipped the whole thing over, put another piece on top, and I pressed it until the rod was all the way through.
I love how carefully he just moves everything. It's so methodical and relaxing, and how you would need to be when you hold this sort of stuff. No jittery fingers here.
At first, I was pretty happy with it, but when I got a closer look, it wasn't as beautiful as I thought. Also, when I tried to move it, a small piece of it broke off. I think this happened because I was unfortunately missing a piece of my die set. I was supposed to have 2 of those metal spacers where one of them would have been put underneath the powder. I think this just really helps keep everything together when the whole thing's flipped over and the pellet's getting pushed out. I then carefully tried to put it onto a small piece that I cut from a fire brick. Unfortunately though, a much larger piece ended up breaking off, and this kinda just made me want to remake the whole thing. However, when I flipped it over, it didn't seem that bad. So, I decided to just roll with what I had, and I loaded this back into the furnace. Now, as I said before, one of the major purposes of this second heating step was to oxygenate it as much as possible. Another very important thing that it was doing, though, was something called sintering. The pellet that I had now was just a bunch of powder crushed together, but in the high heat, the particles should fuse. Then, as it slowly cooled, it should crystallize, which, like I said before, was very important.
"28 hours.
When it was done, it looked exactly the same, and like before, I carefully pushed it out with a glass rod. The pellet that I had now was way stronger than before.
Shinier.
I was used to it being super fragile, so I was still really careful with it. Regardless of all that though, what I had at this point should have been the final YBCO. So now, I was really anxious to test it out, and to see if it actually worked. Like before,
I would be too, after putting, what was that, 28 hours times 2, plus all the original prep and everything. Man, this is a lot of time and money investment, him getting that furnace, getting all that equipment. Man,
I filled a dish with some liquid nitrogen and I dropped in the pellet and I waited for it to cool down. I then got a small magnet and I carefully dropped it on top, and it actually worked.
Cool.
It was floating, just like how I saw in the video,
That's
and
so
I was
awesome.
honestly really surprised that I was able to do it on my first real attempt. Also, this whole time, I was kind of still a bit worried about the purity of my yttrium and copper nitrate, but they were clearly fine. Up until now, I've referred to the floating magnet as anti-gravity magic, but unfortunately, it isn't anti-gravity, and it also isn't magic.
Nah.
When superconductors were first discovered, it was believed that they were basically just super good at conducting. It was found that they had effectively no resistance and they could move an electrical current with almost perfect efficiency. However, it was then discovered that they were a bit more complicated than that. It was also found that superconductors were almost perfectly diamagnetic. This meant that instead of being attracted to a magnet,
Repulsive.
they were strongly repelled. In my case, when the magnetic field of the magnet is applied to my little YBCO pellet, an opposing magnetic field is induced in the YBCO, and it pushes back on the magnet. This induced field perfectly cancels out the field of the magnet, and it causes it to float. This effect alone, though, would just repel the magnet and cause it to fall off.
So again, here's a practical explanation of what we can do with these superconductors, and that is create nuclear fusion. So nuclear fusion, you have hydrogen isotopes heated to several hundreds of millions of degrees Celsius in order to form that plasma. And these superconducting magnets, they create this donut-shaped magnetic field that in order to trap and stabilize the plasma, and you don't want it to touch the actual walls of the reactor, because that can cause the plasma to escape some of its confinement. And the concern there is you just not being able to sustain your reaction. It's not a big safety thing like breaking a reactor containment building or anything like that. So this magnetic field, it compresses this plasma at an extremely high pressure, and plasma is already at a very high temperature. So this achieves the conditions necessary for nuclear fusion. And if it does that for long enough, that's the third thing you need. So again, the temperature from the plasma, the pressure from the magnetic fields, and the time. So you have to sustain these magnetic fields, which is why superconductors are so crucial for something like nuclear fusion. Is then the hydrogen nuclei fuse, and it releases a whole bunch of energy, and ultimately, it's just like anything else that uses energy, right? You can hook it up to the same steam generating system that you would at a regular nuclear power plant or a gas plant or even a coal plant. I don't like coal plants, but the same sort of steam cycle, and you make electricity. Just with fusion, you're making a lot of it.
But it doesn't, because there's actually another unique effect that's going on at the same time. The crystal structure of the YBCO isn't perfect, and small defects allow a bit of magnetic field to still get through. This causes small magnetic flux tubes to form, and they kind of act like tethers, and they hold the magnet in place. This is called flux pinning, and unlike the diamagnetism, the force is actually attractive. So even though the magnet's just floating there, it's still kind of connected to the YBCO, and if I push it around, the pellet moves with it.
I mean, it's both attractive and repulsive forces when you have this electromagnet system. Also, it'd be different if you just arrange them in a circular shape, because then it's kind of because then it would kind of be a. It's different when you surround it. Is what I'm trying to say, and how it will pin it in there while at the same time being repulsive. So the net result is what you see. It keeps it at a certain distance.
Now, another thing to check is to see what happens if I put the magnet on before cooling it. When I did this, it didn't do anything for a while, and then it suddenly jumped into the air. This is called the Meissner effect.
That's cool.
And it's unique to superconductors. It happens because at first, the magnetic field is able to pass through the YBCO. This changes, though, the moment that it gets colder than the critical temperature, and it becomes a superconductor.
Love it when other people bring in more definitions of the word critical. In the context of superconductors, it's when the resistance goes away, and at that point it essentially becomes a true superconductor. So again, another example where critical does not mean the reactor is about to explode like you see in some movies. By the way, according to nuclear reactors, saying a reactor is critical just means it's on. So it's actually very similar to that because it means the superconductor is on and it's being a superconductor.
It suddenly becomes almost perfectly diamagnetic, and it starts expelling almost all of the magnetic field. Okay, so this first run turned out to be way more successful than I expected. The pellet that I had made, though, was kind of ugly, and I still had a bunch of oxide powder.
Make it
The
pretty.
next thing that I wanted to do was use the rest of it and to make several, hopefully nicer pellets. To do this, I figured I had to just more or less repeat the exact same process. This time, I felt that it was probably fine to fill the tube a lot more, and I added about 10 times the amount. However, this was only about 70% of the powder that I had left, so after this, I would still have to do one other run. When it was done, I dumped it all out, and it was definitely a lot blacker than it was before.
Wow.
However, it looked like it still had some unreacted brown stuff in it. When I crushed it up, it looked okay, but I didn't like this at all, and I decided to run it again. I put it all back into the furnace, and I ran it for another 28 hours, and this
How much time?
It was much better. Looking at it now on video, it's kind of hard to tell, but in person, it was definitely a lot blacker. I then ran the last 30% of the powder, and I also did it twice, and I combined it all together. After that, I went back to my fire brick, and I cut out a much bigger piece. I sized it to be the biggest thing that I could fit in the furnace, and it looked like it could hold 5 pellets. So, that was how many I was going to make. Now, in terms of pellet thickness, I had to decide how big I wanted them to be. For the first one, I just crushed what I had, and it ended up being about 1.9 millimeters. But now, knowing that it was 1.9 millimeters and that it weighed 3.85 grams, I could calculate the amount that I needed for any thickness. The 1.9 millimeters did seem to be okay, but I felt that it was just a bit too thin and fragile. So, I decided to make it 3 millimeters instead. I also found that spacer piece that I was missing, and I was able to make some really nice pellets. After making 4 of them, I decided for the last one that I would make it a lot thicker.
Looks like superconductor checkers in the last one he just said king me on. That's awesome. To give you a sense of why you need superconductors, or why it would be better to have superconductors, is a tokamak has a massive magnetic field. You need a massive magnetic field for a nuclear fusion reactor. And by massive, I'm talking 13 Tesla. And Tesla's a really big unit. Usually things are on the order of micro-Teslas when you're measuring magnetic fields. To give you a sense, it's about 200, 300,000 times stronger than the Earth's natural magnetic field. Granted, it ain't as big, but just the intensity of that magnetic field.
This one was 6 millimeters, and I wanted to see if it could float the magnet higher. I again loaded it all into my furnace, and I ran it through a cycle.
Another 28 hours.
When it was done, they all looked good, and I was pretty excited that I now had 5 nice superconductors. I had to test them though, just to make sure they all worked, so I soaked one of them in liquid nitrogen. I then got the same magnet that I used before, and I was disappointed to say the least.
What?
I thought that maybe it was just this one in particular, so I tried all the others and the big one, but they all completely failed. This was a very sad result, and I wasn't exactly sure what had gone wrong. The one thing that I knew, though, was that my base oxide powder was good because I did have one successful run
You had
with
it work before.
So to me, the only possible difference was the level of oxygenation. I had used a lot more powder this time, and I think there was just some trouble getting it all fully oxidized. I figured that there was literally only one thing that I could try, and that was to oxidize it a bit more. To do this, I had to turn all my beautiful pellets back into a powder, and I started by just trying to crush them by hand. It worked okay to break it up into small bits, but these bits were way too hard, and I wasn't able to crush them into a powder.
Wow.
So instead, I threw them all into a small blender. Then after that, I screwed the top on, and I ran it for several minutes.
Blending superconductors. Who knew?
This gave me a relatively fine powder, which I loaded back into the furnace. The powder this time was way denser than before, so I was able to spread it out all in a thin layer at the bottom. I ran it overnight for the same 28-hour cycle, and the next day, it looked about the same as before. I then crushed them all back into pellets, and I again made 4 of them that were 3 millimeters. This time, though, the last one was more like 4.5 millimeters instead of 6. This happened because while reprocessing it, I somehow lost 4 grams of the YBCO. I really have no idea where it went because it's not like I dropped any, and I think that some of it might have just gotten vaporized in the furnace. But either way, I then sintered them, and I was really hoping that this was the last time I was gonna have to put them in the furnace. I took them out the next day, and like before, I thought they looked really nice. That didn't really matter though if they didn't work, so I took one of them and I soaked it in liquid nitrogen. When it seemed cold enough, I then got my magnet, and I was honestly really nervous that it was just gonna fall and hit the YBCO. Also, if this didn't work, then I'd have literally no idea what went wrong or how to fix it. Thankfully, though, it did end up working, and I honestly can't say how relieved I was to see this. Like I just said, if it didn't work, I'd have no idea what to do next, but I guess it really was just the oxygenation.
Sometimes you just gotta try it again. Wow.
I then tested each one to make sure that they were all good, and I also tried out the big one. One thing that I noticed, though, was that none of them floated the magnet as high as that first successful run. Also, the big one seemed to actually be weaker. To me, this meant that even though it was working now, it was still probably lacking oxygen. I really didn't want to have to run them in the furnace again.
That's so cool the way it spins.
One last time. I didn't do them all though, and I just loaded up the big one and one smaller one. This time, I also decided to run it for much longer, and instead of 10 hours at 920C, I did it for 24. I honestly didn't expect too much to change, but there was actually a huge difference. On the smaller one, the magnet floated significantly higher than before.
That's cool.
It was also able to hold a much larger magnet, which I thought was pretty impressive.
Whoa.
The big one was now actually more powerful than the smaller ones, and it had no problem holding the bigger magnet. It could even keep it up when it was on the side, and it had enough clearance that it was still able to rotate.
All right, just got need to make enough of these, and then you can make a fusion reactor. Not really.
At this point, I felt that I was more or less done, and I was really happy with how it had all turned out. However, there was something important that I still had to try. Up until now, I had always put a magnet above the YBCO, but it should also be possible to do it the other way around. To try this out, I set up
Oh,
a
yeah.
magnet track, and when the YBCO was fully cooled, I dropped it on.
Floating
It was
superconductors.
actually able to hold itself up, and when I pushed it,
That's so
it moved
cool.
along the track without falling off.
It's extreme air hockey, magnet hockey.
I was also able to shake the whole thing and bounce it back and forth, and it kind of felt like I was playing Pong. The moment that it warmed up, though, and got above the critical temperature, it
It's
would
gonna
just
fall.
fall off. Now, as one final thing, I wanted to try adding ferrofluid to the magnet while it was floating above the YBCO.
So supercritical, I guess, would be shutting down the magnet reaction at this point, the whole superconductor thing, because supercritical in the context of nuclear reactors is raising reactor power, and subcritical is lowering reactor power. You also refer to a shutdown reactor as subcritical. But in this case, subcritical, I guess, would be subcooling below the critical temperature and having a superconductor. So it's backwards.
I'd seen this in a few videos, and I just thought that it was cool. I also thought that
It's
it was
incredibly
an
cool.
interesting crossover between my own projects because I could use the ferrofluid that I had made myself. I'd made this ferrofluid over
Whoa.
a year ago now, but it's still perfectly good. While I was doing this, I realized that the one big thing that I still hadn't made myself was a magnet. So for my next big project, I've decided to try and make my own neodymium magnets. However, I haven't even started on that, and I have no idea
Look at those
when
crystals.
it's actually going to happen.
That is so cool. Never seen anyone try to synthesize superconductors. Never even got to really see any. I never did much fusion research or anything with that. I mean, obviously I know basic concepts and what the goals are. That is so cool. And this technology, I mean, it can go far beyond just nuclear fusion. I mean, it can be stuff like maglev trains, radiological imaging, the fusion reactors I mentioned earlier, or just very low loss transmission lines, and all this amazing stuff to drive human progress. Thank you so much for recommending this video. This is really, really cool. I'd love to see how this technology continues to develop. Thank you very much for watching. I'll see you next time.